Hi, my name is Fernando. I'm a professor at UFMG in Brazil, and today I will present to you the paper Exploring the Space of Optimization Sequences for Code Size Reduction Insights and Tools. A work that I did in collaboration with Bernardo Lima from UFMG and Anderson Faustino from the State University of Maringá. The main goal of this paper is to describe a strategy to explore the space of optimization sequences for code size reduction. In this paper, we introduce the notion of optimization cache and covering set. An optimization cache is a table of programs to optimization sequences that can be used to support predictive compilation. Entries in this table are numeric representations of programs. These entries are mapped to sequences of optimizations that are good for that program. And the covering set is a small ensemble of optimization sequences that, once combined, tend to be good for any program. And that will be the main topic of this presentation. In our study, we found 22 small sequences for LLVM. These sequences are good for a code size reduction. This space that we need to explore is formed by every possible sequence of optimizations that can be applied onto programs. Note that the same optimization can be applied multiple times onto the same program. Thus, we can have some very large sequences of optimizations, like this one produced by Clang minus OZ, or short sequences. So any vector, any list of these sequences is a point in the search space of optimizations of the LLVM compiler. And such a space can be defined for any compiler. It suffices to build all the possible combinations of its optimizations. Notice that the optimization space is infinitely large because the same optimization can be applied multiple times on the same program, always with new effects. To understand a bit better this space of optimizations, we need benchmarks. But we want programs that are likely to be representatives of every program that could be written by a rational programmer. Fortunately, today it's relatively easy to get a large number of compilable programs. We have used to this end the benchmarks from EngaBench. The paper describing these benchmarks was presented at CGO this year. EngaBench contains 1 million programs. We cannot use them all, so we had to do some filtering. To perform this filtering, we started selecting the largest 15,000 programs from EngaBench. Size is measured in number of LLVM instructions of programs compiled without optimizations. From this group of 15,000 programs, we select 1,500 representatives. For this purpose, we cluster the 15,000 programs. To cluster them, we transform them into vectors. These vectors are formed by program features like number of loops, number of arithmetic instructions, and such. We have used 56 features. We used k-means to find these k-100 clusters. In other words, k-means will give us 1,500 centroids among those 15,000 vectors. Each centroid will be a representative program. So we have now a new benchmark suite with 1,500 programs. The hope is that these programs contain a good mix of program features. With these benchmarks, we can start playing with the optimization space. For instance, the probability of finding good optimization sequences by randomly sampling the optimization space is non-negligible, albeit small. In other words, let's pick up a program P, any program will do. Now let's compile this program with OPT minus OZ. OZ is one of the 2 default optimization levels in LLVM used to reduce code size. That will give us an assembly file. Let's call it O. Now let's look into the universe of possible optimizations. This universe is infinite, of course. Let's then only consider the subset of this universe formed by sequences of 100 optimizations. Now let's draw one random sequence from this universe. Let's call it S. Now, if I apply S onto P, then I will get a new assembly file. This file, I will call it O prime. It's likely that O prime will be different from O. Given these definitions, the probability of having O prime, the program produced by S, being smaller than O is about 10% if we consider that we're beating OPT minus OZ for a given program. We can arrive at such results given a sufficiently large number of benchmarks as a consequence of Chebyshev's inequality. If you want to know more about this methodology, you can read our paper. Anyways, because there are so many points in the search space, finding good optimization sequences requires some guided methodology. As an exercise, let's contrast a guided exploration methodology with random sampling. To this end, we chose to evaluate the implementation of a classic genetic algorithm. We have implemented our algorithm using Pygmo. That's a library that's open source, is implemented in Python. Now let's see how effective is the genetic algorithm as a technique to find good optimization sequences. This figure shows the number of times each method wins, including ties, in a universe of 1500 programs. Winning means generating the smallest program. Rx means drawing X random sequences of 100 optimizations per program, like R10 means 10 random sequences of 100 optimizations. Thus, these results indicate that LLVM default optimization levels are roughly equivalent to drawing 50 random optimization sequences of 100 elements each. In addition, the guided methodology is substantially better than random sampling. It got the shortest program 1,130 times in 1,500 tries. In the end, our study reveals that default optimization sequences adopted in mainstream compilers, they tend to be good for most programs when compared with random optimization sequences. However, the sequences can be very bad for some programs. So, how many default sequences a compiler should have so that at least one of them would be good for most of the programs? This small set of sequences that contains at least one sequence that's good for any program is called a default covering set. Finding a default cover might not be possible because the baseline may outperform every other optimization sequence for some program. Yet, there are some heuristics to find covering sets and to approximate them. We have used Pirini's algorithm to find sequences for code size reduction. To find this covering set, we start building the so-called performance matrix. In this matrix, the rows refer to training programs. The columns refer to candidate sequences. Mij is 1 if sequence J beats the baseline for program I. Using Pirini's algorithm, we got 22 sequences that almost cover the entire set of 1,500 programs. And now we want to analyze the quality of the code produced with the sequences in the cover set. The question is, how effective is a cover set when compared to the baseline? As baselines, we have used Clang minus OZ, Clang minus OS, OPT minus OZ, and OPT minus OS. This figure shows the average variation in the number of LLVM instructions produced by our covering set when compared to different default sequences. We are considering averages for the 30 benchmarks in the MyBench collection. On average, that means that when using the 22 sequences in the cover set, we get code that usually shorter than the code produced by OPT minus OS. Positive numbers in this chart indicate that we got shorter code in number of LLVM instructions on average. And we tend to beat Clang minus OS by a larger margin. And we are also doing a bit better than OPT minus OZ and a bit better than Clang minus OZ. We reduced programs by 47 instructions on average. But notice that the comparison is a bit unfair because we use OPT to run our sequences, whereas Clang -OZ adds some pragmas like non-unrow and non-inline in the program, whereas OPT is language agnostic. The good comparison is thus with OPT, and in this case we do much better. To conclude, in this paper, we have explored the optimization space of LVM 10.0, guided by code size as the objective function. Among the insights that we have acquired in this exercise, we mentioned the observation that the default optimization levels available in the compiler, -OS, -OZ, they tend to be good for most programs. However, they perform rather poorly for a few. Throughout the paper, we have discussed 3 strategies to improve on these default levels, the optimization caches and the covering sets. The 22 sequences in default covering set that we have produced in this paper are rather small. They range from 5 to 19 optimizations with an average of 11 optimizations. Furthermore, techniques like those described in our paper, they can be used to find effective default sequences for other compilers. Applying all of them onto a target program to choose the best results is not really practical because the sequences tend to be very short. And if you are interested in this work, please get in touch. Our code is publicly available in case you want to contribute to reuse it. And we have an artifact available at Zenode. And I think that concludes the presentation. Thank you.